Homework last night was worksheet number 8, questions 9 to 12. We want to go over 2 of them, the first one and the last one, number 9 and number 12, starting with number 9. It says 3 charges in a straight row. First charge is a value of positive 2.5, second one negative 4, and is 60 millimeters to the right of the first one. Third one is positive 3.0 and is 5 centimeters to the right of the second. Got to be careful with these units, especially because not only because we have non-standard units, but because we have different non-standard units. We've got centimeters and we've got millimeters, both in the same question. So we have to be really, really conscious of that here. Let's draw the picture. First one is, we'll call it number 1, and it's positive 2.50 times 10 to the negative 2 coulombs. There's charge number 2, which is 60 millimeters to the right of charge number 1. Its charge is negative 4.00 times 10 to the negative 2 coulombs. And 60 millimeters is, we could say 60 times 10 to the minus 3, tack on a 10 to the minus 3 on the end of it, or you could say 0.060 meters. Either one of those, okay, whatever works for you. 60 times 10 to the minus 3 or 0.06 meters. Now we get the third one that is 3.00 times 10 to the negative 2 coulombs, 5 centimeters to the right of the second one. So we're going to make that positive 3.00 times 10 to the negative 2 coulombs, and 5 centimeters is 0.0500 meters. We want to find the field strength. Man, we're going to find the field strength out here, 2 centimeters to the right of the third charge. So 0.020 meters to the right of that third charge. All right, first of all, answer this question for me, please. What's the charge of that point X? What is the charge of that point X? There's nothing there, right? It's just a point. I mean, it's conceivable that there could be a charge there, but if there is, we certainly don't know anything about it. So we have to assume that there isn't anything there. It's just a point. It's just a point in space. But there is a field there due to 3 other charges. And we can find that field by finding the individual fields. Firstly, the directions of the individual fields. Let's take the black one here, caused by charge number 1. Which way is it going to point? If we pretend 2 and 3 don't exist for a second, only number 1 is there. Which way does the field caused by number 1 point? To the left or right? Sam? It's pointing to the right. And why, Sam, does it point to the right? Yeah. The field points in the way that a positive particle would move if it was placed in the field. And if we put a positive there, it would move to the right because it would go away from the positive, right? Field goes away from positive toward the negative. All right, let's look at field number 2. The green one here. Does it point, forget number 1 and 3 now for a second here. Number 1 and 3 don't exist for us right now. Number 2, does it point away from or toward the negative producer there? Good. It's going to point toward the negative producer. So we're going to say that's going to be E2. And number 3, it's going to point which way as a result of a positive producer? Daniel, which way is it going to point here? To the right, away from the positive producer. So we're going to make that E3. Good. So we got 2 of them to the right, and we got 1 of them to the left. Now we have to calculate each one of those values. And that's not crazy hard, but we do have to be careful to combine some distances here. We're going to say E1, the electric field 1, is KQ over R squared, or 8.99 times 10 to the 9, times Q, which is 2.5 times 10 to the negative 2, divided by the distance here, which is 0.06 plus 0.05 plus 0.02, which gives me I don't have the number on my sheet here, but I think that's 0.13, isn't it? 0.13 meters squared. I'm not going to type in the rest of them. I'll show you the work for the rest of them. I won't type in the rest of them. I'll type in this one, though, just to make sure that you can put into your calculators correctly. We got 8.99. Remember that second function EE? Don't use that times 10 to the thing, okay? Second function EE, 9 times 2.5, second function EE, neg 2. I usually press equals there on the top and then divide it by 0.13 squared. I don't need brackets on the bottom if I'm squaring that number. If I was going to use scientific notation, though, I'd probably want to stick brackets in there if I was squaring something that was scientific notation here. When I do that, I get 1.32988 times 10 to the 10. 1.3299 times 10 to the 10. We could say newtons per coulomb. Although we did learn a new set of units for electric field yesterday. Do you guys remember what those were? It was after this, but we could still use it with this because it means the same thing. Yeah, cool. Yeah, good. Volts per meter. So 1.32 newtons per coulomb, 1.32 volts per meter. Both would be fine. All right, let's find the second one now. E2. It's KQ over R squared. It's 8.99 times 10 to the 9 times, what's my charge here? -4 times 10 to the -2. Is that right? Is that right? What's wrong, Aspen? Pardon me? Right. We shouldn't put the negative in there. We're going to drop the sign of the charge because we don't want to get that mixed up with a negative direction. Now, as it would turn out in this particular case, we'd get a negative field which happens to be pointing to the left, but that would only be a coincidence. So we want to avoid that. My distance here is 0.05 plus 0.02 or 0.07 meters. We square that, do the math on this one, and we get 7.3388 times 10 to the 10 newtons per coulomb. And then the third one, we're going to say E3 is equal to 8.99 times 10 to the 9 times the charge of charge 3, which 3.00 times 10 to the -2, and divided by the distance, which is just 0.02. For a field there, we get 6.7425 times 10 to the 11 newtons per coulomb. All right, now what do we got to do with them? We got to add them up now. What's positive, what's negative? Yeah, David? Yeah, I'd probably make the ones to the right positive, and then there's only one to the left, the green one, make it negative. You could go the other way around, right? As long as right is one sign and left is the other sign, but usually we'd say right is positive, left is negative. So add them up here. We're going to say black plus negative green plus positive blue. When we add all those up, we end up getting a net field of 6.14 times 10 to the 11 newtons per coulomb. How many people ended up getting that? Good. Yeah, I would suggest to you that any question you get on your test or quiz or anything like that probably wouldn't be, on this topic at least, probably wouldn't be harder than question number 9. Okay. Here's a question for you, Ashley. Just a little aside with the whole electric field, more than one charge. We haven't done a question like this, but you never know. Could appear. What if we had something like this? This is, let's say, 2.0 times 10 to the -9 coulombs. Let's say charge number 2 up here is 3.0 times 10 to the -9 coulombs. And we want to find the field strength right here. Let's make this one negative, actually. How do you do that one? I mean, you have to have distances there, right? And you have to have this distance here and this distance right here. How'd you deal with that? You know this, right? How would you deal with this? Yeah. X and Y values. Even before we do anything X and Y, though, draw your diagram, right? Not your free body diagram because it doesn't show forces, but draw your diagram that shows fields. We would have a field pointing to the right, away from the positive, E1. We would have a field pointing upwards toward the negative. We'll call that E2. And then we would just combine them, right? E1 plus E2. And we'd find the net field by taking the hypotenuse, right? That wouldn't be harder, would it? A little bit more work because it's not just adding positives and negatives, it's adding them vectorially using the Pythagorean theorem. But and the last question that we want to go over is question number 12. This is dealing with electric fields, but in a different scenario. You remember that uh, in the scenario we were just dealing with point charges, that produced a non-uniform electric field. And in a non-uniform electric field, I was allowed to use this equation if I knew something about what caused the non-uniform electric field, or I was allowed to use this equation if I knew something about what experienced the non-uniform electric field. But now I'm dealing with a uniform electric field, an electric field between parallel plates, or maybe between the cloud and the ground, something that approximates parallel plates. I'm not allowed to use the first one anymore. Okay, I can't do that because that's the producer equation, but only for non-uniform fields. Now I have to have another producer equation. This is a producer equation as well, but it's a producer equation for uniform fields. So I've now got these two equations valid for non-uniform fields, and I've got these two equations that are valid for uniform fields. So now when I go through question number 12, I know that I'm allowed to use the bottom two if they fit the givens, but I'm not allowed under any circumstances to use the top one, even if it looks like it fits the givens. I can't do it because it's not valid in that situation. All right? Now, one quick little thing before we go about solving number 12. We had two new variables yesterday when we introduced that new producer equation, the uniform field producer equation. Delta D stood for, you guys remember that? Distance between the plates. So not the distance a charge has traveled, not the distance from the charge to the top plate or from the charge to the bottom plate, but the distance from the bottom plate to the top plate, the distance between the plates. And delta V stood for, this one's the harder one. Delta V stood for the, sorry? Yeah, it's the volts, yeah. The term for that is called it's called the potential difference. And the potential difference, you might remember from yesterday, is the difference in energy per coulomb of charge. So it's related to energy, clearly related to energy, but it's not energy. The energy is in joules. Potential difference is in volts. It's energy per coulomb of charge. It's like the analogy yesterday, the money per person, not the $100 that we have together, but the $4 that we have per person. All right, let's take a look at this question now, number 12. It says an electron sits between two charged parallel plates 10 centimeters apart. The field strength between the plates is 2.5 times 10 to the 3. So we've already got the electric field strength. We want to find the potential difference here. The distance between the plates, I'm going to convert to meters. We have the electric field. Remember, I want to put that arrow over it to remind me that it's not energy. The electric field is 2.50 times 10 to the 3. We also have the fact that this is an electron, so we know the charge and the mass of the electron. I'm not going to write those values down because I'm not sure that I'm going to need them, but I'm going to just write the terms down just to remind me that I have them if I do need them. Let's find the potential difference here. Well, the bottom two equations are allowed to be used here. Looks like the bottom one is the one that's going to fit here. E is equal to delta V over delta D. Now when I rearrange this to solve for delta V, I get E, the electric field, times delta D, the distance between the plates. Every once in a while, I make a mistake just because I'm being careless and put a little arrow over it. What's wrong with that? Like, what does that arrow infer? Yeah. Yeah, that's displacement. That's how far something's moved, right? So that's dead wrong. To put the arrow over it, that's dead wrong. We're not talking about how far something's moved at all. We're talking about the distance between the plates. All right, so E is 2.50 times 10 to the 3. And the distance between the plates is 0.100, which if we do the math there, works out to be 2.50 times 10 to the 2, I believe. Yeah. And what would the units be for that? Potential difference? It's going to be volts, right? Or if we're talking about a volt being energy per coulomb, we could also say 2.50 times 10 to the 2 joules per coulomb. It would be exactly the same thing. Volts, joules per coulomb, whatever works there, right? What's the magnitude of the electric force experienced by the electron? Well, look, we got another equation that we're allowed to use. What's circled in green there? E is equal to F over Q. I'm not going to write down my givens again because I've already done that. I'm going to rearrange this to solve for F. Evan, how am I going to rearrange that to solve for F? Yeah, it's Q times E, right? We're dividing by Q. To get rid of it, we got to multiply by Q. So what do we got here? The charge of an electron is 1.60 times 10 to the minus 19. Negative, right? But we drop the sign of the charge. E is 2.50 times 10 to the 3. And when we do the math on that one, it works out to be 4.00 times 10 to the negative 16. And the units for that would be newtons. And finally, C, the acceleration. This is a great question. Number 12 is a great question because really it asks you everything for parallel plates, right? Like the electric field, using the electric field equation, but also the force and then also the acceleration. Like what else could I really ask you for parallel plates other than maybe direction, and so on here. A is equal to F over M. F is 4.00 times 10 to the negative 16. We calculated that just a second ago, and the mass of the electron is 9.11 times 10 to the minus 31 on our data sheet. Gives us 4.39 times 10 to the 14. We would expect a big value, right? Because we're talking about something with a really, really, really small mass. Big acceleration because it's such a small mass. All right. Let's say I have two parallel plates. Actually, let's make them vertical this time because we always seem to draw them horizontal, right? Let's say that the left plate is negative and the right plate is positive. Tell me which way the electric field points here. Which way does the electric field, James? Which way does it go? Good. Goes from right to left. Goes from positive to negative. What kind of electric field is it? Uniform or non-uniform? It's a uniform electric field, and because of that, I'm allowed to use those last two equations. E is equal to F over Q, and E is equal to delta V over delta D. If I put a negative charge right there, and it's initially moving downwards, which way is the force acting on this particle? Which way is the force acting on this particle? Down? That is the electric force. There would be a gravitational force acting downwards on it, right? But in the absence of gravity right now, which way is the electric force acting? Cool? It's acting to the right, opposite to the direction of the electric field because it's a negative particle. So that means the path that it's going to take is going to be this. Vertically, it's got gravity acting on it, right? What kind of motion does it experience vertically? Is it moving at a constant velocity? Is it accelerating? In other words, is it uniform motion or is it accelerating? Vertically, because of gravity. It's accelerating because of gravity. Horizontally, is it traveling at a constant speed, constant velocity, uniform motion, or is it accelerating horizontally? Yeah. No, it's accelerating. It's accelerating because you have an electric force acting to the right, just like you have a gravitational force acting downwards. Okay, does that make sense? Couple more questions. Let's say we've got a positive particle right here. Let's say the force on this positive particle, however we happen to know this, is, let's make it 2.0 times 10 to the negative 10 newtons. Okay, there's the force on that positive particle. Here's another positive particle that has the exact same charge. What's the force on that one? Same thing? Is it? It's in a different spot. Is it the same force? Absolutely it is. Absolutely it is. Look, E is equal to F over Q. Therefore, F is equal to Q times E. If the charge is the same, and the field is the same, then the force has got to be the same as well, right? Everywhere in between those plates, the force is going to be the same. What if this guy is a lot heavier than this guy? Is that going to change the force? No, because the force is dependent upon charge in the electric field. If this guy is a lot heavier than this guy, is the acceleration going to be different? Yes. So the field is the same, the force is the same, the acceleration could be different depending upon whether the mass is the same or not. That make sense? Okay, let's say that I wanted to plot a graph. Oh, this is a good one. Great question right here. Let's say that I want to plot a graph of electric field versus the position. We're going to say D, not delta D. Okay, not delta D, not electric field versus plate separation, but electric field versus position. Okay, make sense? This is 1D. This is, actually, let's call it R. Okay, this is an R. This is a different R. Delta D is still the same, right? But this is one R. This is another R. What does that graph look like? You know what? I'm going to give you 30 seconds. I want you to sketch that graph on your own paper. Just scrap paper if you want, whatever. Just sketch what you think that graph is going to look like. All right, who wants to tell me what that graph looks like? Anybody want to take a stab at it? Yeah. Straight line like this? Ooh, that's different. How many people agree with that one? Anybody got a different answer for me? He's right. He's absolutely right. Why is it a straight line like this? Yeah. That's right. Where you are, where this charge is in between the plates doesn't make any difference. The electric field is uniform everywhere between these plates. Therefore, however far you are away from plate one, we're calling that distance R here, is not going to affect what the electric field is. The electric field is what it is, depending upon the distance between the plates, but not depending upon how far you are away from one of the plates.